The CBO associated with indirect calorimetry has a series of indications that should be reviewed by the student prior to challenging. You can see how ventilator dependency has a variety of factors associated with it. Of note for indirect calorimetry is that there are no known contraindications to the performance of this procedure, assuming that the patient is off the ventilator for minimal periods of time when setting up the equipment. The limitations associated with this procedure are that the FiO2 must be less than 85% for this unit. As well, the inspiratory and expiratory tidal volume can vary by no more than 30%. This is so that accurate volumes can be used in the calculations. Variable FiO2s, particularly those greater than 80%, bias flows for ventilator triggering, presence of other gases, including nitric oxide, and water in the sampling tubing, as well as dialysis, are all other factors associated with limitations to this procedure. Bear in mind that they can skew your data. Review the chart for an order, as well as for the appropriateness of performing indirect calorimetry on your patient. Obtain the necessary equipment to interface with the Dexometer monitor. This starts with the proper module. Note that it is the COVX module that is specific to this gas sampling system. Other equipment that is necessary for the performance of this procedure is the CO2 sampling line, spirometry line, the appropriate patient connector, as well as the end-tidal CO2 connector. It is suggested that the student familiarize themselves with all the connections of this system prior to the challenging of the CBO. Note that there are specific ports for each of the lines, CO2 sample line, as well as spirometry lines at the patient connecting end, as well as spirometry lines and CO2 sampling lines at the module end. Having a closer look at the pneumatac associated with this module, you'll note that this is a Fleisch pneumatac. A Fleisch pneumatac works on the principles of Ohm's law. With a known resistance, measuring P1 and P2, flow can be derived. The monitor can measure this flow and with an internal timer convert that flow into volume. That volume can then be converted into tidal volumes or minute volumes, depending on the respiratory rate noted. Use aseptic technique throughout the procedure. Wash hands at a sink or with an approved alcohol-based product. And don gloves for all aspects of the procedure at the patient's bedside. Identify the patient, yourself, the department that you represent, and your role as a respiratory therapy student at NBCC SJ. Assemble the equipment according to the manufacturer's specifications. Place the Fleisch pneumatac in place at the patient end, noting how the spirometry lines go back towards the ventilator circuit. This monitor uses touch and turn or turn and click technology. You want to start by hitting the Admit Discharge button. What this does is it allows you to input appropriate patient demographics. The important demographics here are mostly associated with the patient's height and weight. These are necessary for the software within the module to perform necessary calculations based on predictive models for caloric needs and caloric expenditures. Watch here as this is done. By going to the Admit Patient module, demographics are done, height may be adjusted, weight may be adjusted. Note how the body surface area will change. This will help again in some of those predictive models. Next, monitor setup. This will give some input to the monitor as to what to do. Go to Screen 1 Setup, and then select Waveform Fields. I'm going to put an end-tidal CO2 waveform up. By going to Field 1, changing it to CO2, we can now see this in real action. By hitting the Monitor Setup key, Screen 1 Setup comes up, Waveform Field comes up, change Field 1 until it changes to CO2. You should then see a graphical display of the CO2. Now go to Digit Fields, and in Digit Field number 1, for Lower Field 1, change that to EE and RQ for Energy Expenditure and Respiratory Quotient. Field 2 should then read V.O2 for O2 consumption. You'll then see these displayed in the graphical display in the bottom part of the screen. Once again, by using the turn and click technology, by hitting and clicking this button once, you can get into the gas exchange setup. By entering the gas exchange setup, you can change the energy expenditure average time from 2 hours to 24 hours. This is the gold standard for indirect calorimetry sampling, as it takes care of all the diurnal variations associated with O2 consumption and CO2 production. You'll then see how this scale is changed in the EE and RQ average. Speaking of energy expenditure, you can see the ratio of kilocalories to mils of O2. With the VO2 displayed on the front, it's obtained by sampling from the gas ports in A and B. Continuous aspirate of gas through these ports allows the FI and FeO2 to be sampled and analyzed and multiplied times the minute ventilation to give a V.O2. The same procedure is used for carbon dioxide with the analysis of expired and inspired carbon dioxide. Using both pieces of this data, the RQ can be derived, which is indicative of the substrate being burnt. Recall that the respiratory quotient is the ratio of CO2 production to O2 consumption. RQ can be greater than 1, which is indicative of overfeeding that can lead to lipogenesis and prolong ventilatory weaning. Ensure that other personnel is notified as appropriate, including the preceptor to whom you are assigned. Document appropriately, and ensure that you are correlating the findings to the patient condition. By a thorough review of the equipment, its placement within the system, as well as some of the procedural steps outlined in this competency-based objective video, you should be successful in the challenging of this CBO on indirect calorimetry.